explain the losses and efficiency of a DC motor. Before heading into the topic, look at this scenario. Crane is a large and tall machine used to move or lifts the heavy objects. Here, motors play major role for its operation. Crane motors are operated in extreme weather conditions as well as are subjected to high operational requirements. They have to withstand high humidity, salty air, and high wind speeds. And they should ensure a high overload capacity and a wide speed control range. Some crane motors have large duty cycle, that is, they should operate for long duration. These operating conditions are the vital consideration for the motor's efficiency. We have to choose the motor which can operate at better efficiency. For choosing the motor, we need to have the idea of its losses and efficiency. Let us study about these losses and efficiency in detail. The most convenient method to understand the losses in a motor is using the power flow diagram. Initially, the electrical power is given as an input which is converted into mechanical output power. Here, efficiency of the output is affected by some losses. These are copper losses, which are armature copper loss, field copper loss, and brush contact resistance loss. Core losses, which are hysteresis loss and eddy current loss. Mechanical losses, which are bearing friction loss, brush friction loss, and windage loss. This diagram visualizes the amount of power that has been lost in various types of losses and the amount of power which has been actually converted into the output. Let us learn about these losses in detail. The losses produced by the mechanical friction of the machine are called mechanical losses. These losses occur due to friction in the moving parts of the motor like bearing, brushes, etc. Bearing friction loss depends on type of bearings and their lubrication. Brush friction loss occur in between the carbon brush and commutator. For cooling purpose, air is passed through the ventilating ducts of a motor. It also causes some friction. It is known as windage loss or wind friction loss. Now, let us learn about the electrical losses. Core losses are present in all rotating electrical machines. In a motor, iron core of the armature is rotating in the magnetic field, so core losses occur. Normally, motor is operated in constant speed, so these losses are almost constant. These losses are categorized into two forms, hysteresis loss and eddy current loss. Hysteresis loss is the heat loss caused by magnetic properties of the armature. It occurs due to reversal of magnetization of the armature core. It is given by Steinmetz formula. According to this formula, hysteresis loss is given as shown on the screen, where eta is Steinmetz hysteresis coefficient, Bmax is value of maximum flux density, F is the frequency, and V is the volume of core in meter cube. Eddy current loss. If armature of a motor rotates in magnetic field, it will cut the magnetic flux and produce current in the armature coil. Due to this, in the armature core also, small amount of EMF is induced and it produces a current with large magnitude called eddy current. The power loss due to flow of this current is called eddy current loss. Here, the power is dissipated in the form of heat. Eddy current loss WE is given as shown on the screen, where T is thickness of each lamination and K is eddy current constant. We have already learnt these both hysteresis and eddy current losses in detail in the topic Loss and Efficiency of DC Generator. The copper losses are the winding losses that take place during the current flowing through the winding. They occur due to the resistance of the winding. They generate heat that is proportional to the resistance of the conductor. Motor has two windings, armature winding and field winding. Thus, it is categorized into three parts: armature copper loss, field copper loss, and brush contact resistance loss. Armature copper loss is equal to Ia square Ra, where Ra is the resistance of armature and Ia is armature current. This loss is about 20 to 30% of full load losses. Field copper loss for shunt and series motor is shown on the screen, where RSH and RSE is resistance of the shunt and series field winding. ISH is shunt field current and ISE is series field current. This loss is about 30 to 40% of full load losses. Brush contact resistance losses. Brush contact loss occurs due to resistance between the surface of brush and commutator. Magnetic losses and mechanical losses are together known as stray losses. These are also known as rotational losses. Stray losses and shunt copper losses are together known as standing or constant losses. Due to constant field copper loss, stray losses and shunt copper losses are also constant. For shunt and compound motors, field copper loss is constant and armature copper loss is variable. Total loss is equal to variable armature copper loss Ia square Ra plus constant losses Wc. Now, we are going to study the efficiency of a motor. Efficiency is the ratio of motor's output and input. Mechanical efficiency eta m is equal to useful mechanical power output divided by mechanical power developed, that is EBIA, where EB is back EMF and IA is the armature current. Electrical efficiency eta E is equal to mechanical power developed, that is EBIA, divided by total electrical power input, that is VI, where V is the terminal voltage and I is the load current. Overall or commercial efficiency is equal to useful mechanical power output divided by total electrical power input. Obviously, overall efficiency is equal to mechanical efficiency into electrical efficiency. Input of a motor is equal to output plus its total losses, where output is VI and total loss is Ia square Ra plus Wc. Armature current Ia is equal to load current plus shunt field current. V is voltage and I is current. Here, shunt field current is negligible as compared to load current. Therefore, efficiency is equal to output by input. Applying above equations, we can find the efficiency as shown on the screen. Now, efficiency is maximum when denominator is minimum, that is, when denominator is equal to 0 or I square Ra is equal to Wc. Hence, motor efficiency is maximum when variable loss is equal to constant loss. Let us determine the losses and efficiency of a 500 volt DC shunt motor which takes a current of 5 ampere on no load. The armature resistances and armature current are 0.22 ohm and 3 ampere respectively. We have to find the efficiency when loaded and taking a current of 100 ampere. Solution. At no load condition, back EMF is equal to V minus IARA. Shunt current is equal to ampere current minus armature current. Armature copper loss is Ia square Ra. Motor input is equal to Vi. Therefore, constant losses are motor input minus armature copper loss as shown on the screen. Assume this loss is constant under all load conditions. At load condition, motor current is 100 amperes. Armature current is equal to motor current minus shunt current as shown on the screen. Therefore, back EMF and armature copper loss is found as shown on the screen. Hence, total losses are equal to armature copper loss at load plus constant losses. At load condition, motor input is equal to VI and motor output is given as shown on the screen. Therefore, motor efficiency is equal to output divided by input. Summary. This brings us to the end of the lesson. We have learnt about power flow diagram of a DC motor, losses and efficiency of a DC motor.
If you look around your house, you will see many devices that have electric motors, such as kids' toys, table fans, toothbrushes, hair dryers, and this electric cutting knife. But how does the electric motor work? You turn it on and somehow it starts rotating. Why is that? In this video, we'll cover the basics of electricity and magnets, and then put it all together to understand how the motor works. This video is sponsored by Brilliant. Let's start with something called a circuit. You have a battery, some wires, and a device that uses electricity such as a light bulb. Electricity flows through the circuit, but as soon as there is a break in the wire, the electricity stops flowing and the light bulb goes off. The path must be complete for the circuit to work. This is best done through the use of a switch. Electricity is flowing down the wire. This is called conventional flow. If we take the battery out and flip it, then the current will flow the other way. The light bulb will still work in either case, but there are some devices that will work differently depending on which way the current flows. Okay, so that's the basics of a circuit. Now let's come over here. This is a magnet. It has a north pole and a south pole, and it likes to attract other metal objects like these paper clips. If you bring another magnet towards it, opposite poles attract, and the same poles repel. Magnets don't have to be in this shape. For example, some magnets might be more flat like this. You can think of this magnet as always on, it's always working, you can't really turn it off. That's why it's sometimes called a permanent magnet. It's made up of many smaller magnetic domains that are lined up in the same direction. But later I'll show you a type of magnet where this is not always the case. Let's take one of our permanent magnets and drill a hole in the center and put it on something that will allow it to spin. Now bring another magnet towards it. Our spinning magnet will immediately line up until opposite poles are right next to each other. Now switch out the side magnet. The same poles repel and opposite poles attract. If we keep switching out these side magnets, then our spinning magnet will just keep spinning. This concept of the spinning magnet is really important. We'll come back to it in a moment. Here's a metal bolt which is not a magnet. It's made up of magnetic domains, but they are pointing in random directions. Now let's take a wire, wrap it around several times, and then create a circuit. The current through the wires forces the magnetic domains to line up. That means we've just made a magnet, or more specifically, an electromagnet. It can do the same things that a permanent magnet can. It can pick up pieces of metal, and it has a north and a south pole which will attract or repel other magnets. But the electromagnet is special in the sense that it can be turned on or off, just like the light bulb. You can't do that with a permanent magnet. Now watch what happens when we flip the battery. The electric current was flowing this way, but now it flows the other way. This will cause the poles on our magnet to switch places. North will become south, and south will become north. This is called reversing the polarity of an electromagnet. Instead of flipping the battery, an easier way to do this is to just switch the wires. You should be aware that the electromagnet will get very hot if it's on for a while. Just a caution in case this video inspires any science projects. Let's come back to our spinning magnet. This time we'll replace the spinning magnet with our electromagnet. As soon as we connect the wires, the magnet turns on and it lines up with the side magnet. Now, in reality, connecting these wires would prevent the bolt from spinning freely, but what's important here is the concept of the spinning electromagnet. Now let's switch the wires to reverse the poles on the electromagnet. The same poles repel and opposite poles attract. Now reverse the polarity again. Same poles repel and opposite poles attract. If we keep switching the polarity, our electromagnet will just keep spinning. To make this stronger, let's bring in another permanent magnet on the side. Notice how this side has the south pole towards the center, and this side has the north pole towards the center. The side magnets work together to spin the one in the middle. This right here shows the very basics of an electric motor, but we need to make a few improvements. The two side magnets can be replaced with stronger curved magnets. And instead of a bolt with wires, we're going to use a metal loop. This is called the armature. Connect our wires and we have a circuit again. This time you can think of the electromagnet as flat like this with the south pole pointing up. Now the armature will spin until opposite poles are lined up. We can keep it spinning by switching the wires just like we did before. But this is a lot of work to sit here and manually switch these wires. We need to add something to the armature called a commutator. It's a ring with gaps on the opposite sides. The commutator will spin along with the armature. Now we connect the circuit with two brushes on the side. These brushes will slide along as the commutator spins, and they are spring-loaded so that they always maintain contact. The current flows from the wire, through the brush, the commutator ring, the armature loop, and back through the other side. Now we have our electromagnet and the armature spins. As we come around this time, the brushes will switch contact to the other side of the commutator ring. Remember, there's two brushes, so this is happening on both sides. Before the switch, the current in the armature is flowing this way. After the brushes switch sides, current will flow the other way. This means the electromagnet switches polarity, which will cause the armature to keep spinning. This commutator ring does the same thing as switching the wires like we were doing before, but this time it does it all on its own. It will continue to spin as long as we're connected to a battery. Disconnect the battery, no more electromagnet, and the spinning stops. Now so far we've only used one loop on the armature. This will cause our motor to have an irregular speed, and in fact, we could get stuck in this position, with the brushes halfway between commutator segments. What we can do is split the commutator ring and then add another loop. So first, the brushes are in contact with these two commutator segments, which turns on this electromagnet, which causes it to start spin. Wants to spin. The brushes switch contact and the next loop turns on. This keeps happening as our motor spins. It's almost like the loops will take turns being an electromagnet. Some electric motors will add many loops to the armature. This ensures that there will be a continuous spinning motion on the motor. This spinning force on the armature is called a torque. Stronger torque means a faster spin. There are some things we can do to improve the torque of the motor. Electromagnets are stronger when there are more wires. This is true when we wrap more wires around the metal bolt, and it's also true when each of our armature loops are made of many wires. The motor will have stronger electromagnets, which means it will spin faster. If you look at some pictures of real electric motors, you can see lots of wires wrapped around. And yes, this is the same reason. More wires wrapped around means stronger electromagnets. Another way to make this stronger is to use more electricity. Let's learn a few more terms here. The part that doesn't move is called the stator. In this case, it's the two permanent magnets on the side. These fit inside the edges of the motor case. The armature in the middle is also called a rotor. Remember, this is the part that spins. The axle goes through the middle here and then sticks out the back of the motor. What I've shown you in this video is called a DC motor. If you have a device that moves and is powered by a battery, there's a good chance there's a DC motor in it. Other types of electric motors will work a little differently than what I've shown here. No matter the type of motor, most of them will produce some type of spinning motion. Once it's spinning, we can use this to make different devices move. In this case, a kid's toy. Or even a fan that cools your room. The spinning of the motor can be converted to other types of movement, such as the side-to-side motion that we see in this fan. Or how about this electric cutting knife? Each blade is going back and forth. It all starts with the spinning of the motor to turn a gear, which then pushes these two pieces back and forth. So hopefully this video has made a few light bulbs go off in your brain. If you like learning new things, head on over to Brilliant. This is a problem-solving website and app that focuses specifically on math and science. The idea here is that you learn by doing. Pick a topic, it starts with the basics, but gradually it gets more complex as you go. For me, I've enjoyed how you can see these concepts visually, like the area of a circle. You get to see why the equation